Welcome back to 15-Minute Math. So today we're going to talk about this second fundamental theorem of calculus. In a previous video we covered the first. Let's do the statement of the theorem first, and then we'll go into a little more detail. So if f is continuous on the interval a to b, then the definite integral from b to a of f of x dx is equal to capital F of b minus capital F of a. And the statement says that capital F then is any antiderivative of f. So basically capital F is any function that when you take the derivative of it, you get little f here. Which is kind of interesting, because this theorem says that if I can find an antiderivative of f, I can just kind of evaluate the endpoints of that interval, or I should say the function values of that antiderivative at the endpoints of that interval, and that should tell me the area under the curve during that interval of the original function, which is interesting. To me, this is not nearly as obvious as the first fundamental theorem. And so I think the best way to approach this, to be able to kind of understand why this should be true, is to come up with an example, kind of more of a physical example. So one thing that we talked about in earlier videos when we were dealing with derivatives was the relationship between velocity and displacement. So remember that velocity is just the derivative of displacement, which is to say that velocity tells you the rate at which you are changing distance. Which should make some sense, right? Because if you're moving fast, if you have a high velocity, your distance is changing, I should say displacement. Your displacement is changing quickly, whereas if you're moving slowly and you have a low velocity, your displacement is moving, it's changing very slowly. So velocity is just the rate of change of displacement. And so maybe we could write this down where let's say S of t is our displacement. Then we'll call V of t our velocity. That one actually makes some sense. So the relationship we need to remember is that S of t, I was going to say this backwards. V of t is the derivative of S of t, which is to say the velocity is the derivative of the displacement. So let's try to solve a problem. Let's say that we wanted to know our change in displacement. We want delta S for the interval 0.5 to 2. So 0.5, we're here. 2 here. We want to know S of 2 minus S of 0.5. We want to know the change in our displacement over that time interval. Now, of course, we can see on the graph and at least estimate, right? And you just take one minus the other, 80 minus 5, it looks like. It looks like we're going to get 75. Definitely we could do it that way, but I want to do it a different way. I want to think about the relationship between velocity and displacement and try to see if we can think about a different way that we could come up with this same solution. So what I'm going to do is I want to think about also what would be our velocity if this is our displacement graph. Let's go ahead and give a formula here. Our displacement function is going to be given by 20t squared. And if we remember our relationship here, that means our velocity function is just the derivative. We can use the power rule. It's just going to be 40t, so we're going to have a linear function. So we can graph that, 0, 0, 40, 1, 80, 2. We're going to get a graph that kind of looks something like this. Hopefully a little straighter than what I can draw, but you get the picture. Okay. And instead of actually getting the exact area, although we could, because that's a pretty simple geometric formula, let's use a technique we introduced a couple videos back where we do a Riemann sum. Okay, so we're going to estimate this using rectangles. And since I don't feel like I could draw this accurately, let's just go ahead over to Desmos and do this. So here's our function. Here's our velocity function. And the idea is this. The velocity is constantly changing. So it's going to be hard to get an exact value. What we're going to say is we're going to instead think about it as almost like a step function. Can I guess which one it is? There we go. Hey, there we go. So instead of thinking about this as a velocity that's constantly increasing, let's just pretend that from the interval 0.5 to 1, the velocity was a constant 30. And then from 1 to 1.5, it was constantly 50. And then from 1.5 to 2, it was constantly 70. We could estimate the change in displacement then, right? Because, I mean, that's pretty simple, almost 6th grade math, 5th grade math, whatever you learn to do that. We know that distance is just rate times time. And so if I was going 30 miles per hour for, what's that interval length? Half a second. And then I was going 50 miles per hour for half a second. And then I was going 70 miles per hour for half a second. It's pretty easy to evaluate. That's going to be 15 plus 25 plus 35. What is that? 60, 75. So that would be an estimate of the displacement during that time. Right? Of course, it's just an estimate. You get an overestimate in here, you get an underestimate in here, overestimate, underestimate, yada, yada, yada. But that'd be a decent way to estimate. And we know from previous videos that we can make this estimate better by doing more subintervals. And in fact, we could even let the subintervals go off to infinity and get an exact answer. But just for it to get the point across, that could be definitely what we're doing here. So think about what we're doing. We're finding the area under the velocity curve. We're estimating just so that I can do it somewhat easily. But we're finding the area under the velocity curve from 0.5 to 2. So another way to say that, to find the difference in position from one to the other, think about what I was doing. I was getting an estimate of the integral from 0.5 to 2 of v of t dt. And it turned out to be 75, but that's kind of neither here nor there. Or another way to say that is I was taking the definite integral of the derivative of my displacement function. And remember, I was trying to answer the question, what was my difference in position from s of 2 to s of 0.5? From 2 seconds to 0.5 seconds, what's the difference in position? And my claim, and hopefully you can see why it works, is that this expression is going to give me that, and whichever way you want to say it, it's going to end up being 75. So in order to find this difference, I just integrated the derivative. And I think physically that makes some sense, because like we said, that's something we learn in elementary school, that distance is rate times time. And so if I have a rate and an interval of time that I'm traveling that rate, I could just add those together and get what I'm after. But kind of the powerful thing about this is there's really nothing special about velocity functions and distance functions, or I should say displacement functions. I mean, any mathematical functions that satisfy our original relationship, I'm trying to pull up my whiteboard here, that satisfy that box relationship where one is a derivative of the other, we're going to have that same relationship where if I want to find the difference between, one point and the other, I should say the function value evaluated at one point and another, it suffices to just find the area under the curve of the derivative of that function. And that's exactly what the second fundamental theorem is telling us only usually we kind of go at it from the other angle, in that if we want to find the area under this curve, we come up with some antiderivative, which, remember, an antiderivative is just a function that you can take the derivative of to get to this other function, and I evaluate the function values at the endpoints. So it's saying exactly the same thing. And what I want you to notice is remember our area estimate was 75. But if I do the exact area, it's 75. And notice that if I literally just took the difference of the function values, I mean, that is exactly the same thing, and that's always going to give me the same thing. I can change my interval length. I should be able to change my interval length. Desmos is, it's not going to work here, but I should say, no matter what I put in here, as long as I change it here as well, I should get the same thing. So if I realized that my endpoints were not linked to my sliders. So if I change that to 4 and that to 4, it still works, right? There's nothing special about the example I chose. There was nothing special about the endpoints I chose. We always get this relationship. I could change this to a different function, and it should still work pretty much the same way, provided I get my variables correct. S of t. There we go. Disregard the window. I just want you to notice that this difference is exactly the same as that definite integral. And remember the relationship. V is just the derivative of s prime of t. Or another way to say that is, if I want to evaluate this, all I need to do is find a function that when I take the derivative, I get my original, and then I can just evaluate the endpoints. And so, as an example, let's come up with a pretty simple example here. Find the area from 1 to 4 under the curve 1/3. I'm sorry, I don't want to do that. Let's see. Maybe I want... Yeah, I do want 1/3. Something like this. So let's apply the fundamental theorem. It says if I can find a function that when I take the derivative, I get that, then I can just compute the difference at the endpoints. So for example, if I had, I don't know, t cubed, let's say, think about that. If I took the derivative of t cubed, I would get 3t squared. So maybe t cubed is not the way I want to go. But that's okay. I'll just fix it. What if I took the derivative of 1/9 t cubed? Well, then whenever I take the derivative, 3/9 is 1/3 t squared. So that's the function I'm looking for. The fundamental theorem says all I need to do now is take 1/9 4 cubed minus 1/9 1 cubed. It says I just evaluate this function, take the difference of those function values at those endpoints. And so that's going to be 64/9 minus 1/9. It's going to be 63/9. So now let's talk about this really quickly in conjunction with the first fundamental theorem. So the first fundamental theorem says this. If I take the derivative of an integral, I get the original function back. And now what I want to think about with regards to the second fundamental theorem is, remember, let's introduce some notation in that capital F is going to represent the antiderivative of that right there. Wait, I don't want to say that. I wrote that backwards. I want capital F prime of x. There we go. Capital X is the function that whenever you take the derivative, you get little x. Okay, so the second fundamental theorem says this: if I want to take the integral of a derivative, where derivative is capital X here, I again get my original function back in a way. So here I do the derivative of an integral and get the same function back. Here I do the integral of a derivative and get the same function back. So in our last video we were saying the first fundamental theorem kind of suggests that derivatives and integrals are inverses, but we were only doing it one way. The second fundamental theorem really gives us that other way. And so integrals and derivatives really truly are inverses. And that is kind of the key point whenever we take the two fundamental theorems together. You know, when we got our bag of inverses, we've got multiplication and division, addition and subtraction, logarithms and exponents, and now you can add to that derivatives and integrals. They are true inverses. They undo each other. Doesn't matter which order you do them.